Hey class, let's work on a couple of these examples that were in our notes. Let's do them one more time, just so if you need to see them again. On how to build confidence intervals. Really, there was 4 types of confidence intervals. I'm sorry, take that back. 3 types. 3 types. 2 that we could do if we're trying to estimate a mean, population mean mu. 1 where we know the sigma and 1 where we don't know the sigma. So we'll do one of each of those. And then also, if we're trying to estimate a population proportion, p, using p hat. There is a 4th type. That's what made me think of this, is that you could also, if you have raw data, then you do it a little bit differently, or easier, I should say, where we don't know sigma. So let's do this first one. This is where we have a known sigma. So the example is an M&M factory rep tells us that the population standard deviation of the weight of a bag of M&Ms is 6 grams. So he tells us what the population standard deviation, sigma. So sigma is 6 grams. He refuses to tell us the true population mean, so we decide to estimate it with a sample. We randomly sample 36 bags, so n is 36, and we find a sample mean x bar equal to 40 grams. Build a confidence interval for which we could be 95% certain the true population mean lies. Good, so this is what we got from the problem. So let's figure out what else we need. We need an alpha. Remember, alpha is just 1 minus the confidence level, 0.05. And since z is given to us, or sorry, since sigma is given to us, we could use a z here. We would just ask ourselves, what's the z score for a 95% confidence interval? And I think that's 1.96, like that. We don't have to do that, right? Because we could just find the margin of error without that, in which case we just use this confidence.norm, which asks for 3 things. Alpha, there's alpha, the standard deviation, which is sigma, so not the standard error, but the standard deviation, sigma, and the sample size, 36. And that's it. So that's all we have to do. The confidence.norm will just give us the margin of error. Remember, the margin of error is just really z times some standard error. All right, so let's try it that way. So we can say z times the standard error. Well, we haven't figured out standard error, but we know, we can do it right now. The standard error for, in this case, is just sigma divided by the square root of n, which we'll see is 1 in this case. So we have a standard error equal to 1. So really all that is 1.96, times 1. And it rounds to the same number, 1.96. If we had been more exact here, it would have been right. So it's the same number. So this confidence.norm will give us the same thing. So we could change this up. Let's make the sigma equal to 10, and then it changes a little bit. Make the sigma equal to 15, right? So the margin of error then is not the whole story. We then have to build the upper and lower confidence limit, UCL, LCL, which is just the mean minus, the upper confidence is the mean plus the margin of error. There's x bar plus the margin of error. And the lower confidence limit is x bar minus the margin of error. Done. So that's it. So then we say we are 95% certain that the true population mean, we should change this back, this was 6. Change that back to 6. 95% confident that the true population mean lies between 38.04 grams and 41.96 grams. That's the end of the story. All right, let's do another one. Here's an unknown sigma problem. So this one was in our notes again. We'll do it one more time. So assume we're interested in estimating the mean height of the head of beer we're producing. We take 11 height measurements and find a sample mean to be 1.2. So let's actually, we have n equals 11. We find an x bar from our sample mean equal to 1.2 inches, and a standard deviation of the sample, s, 0.04. So this is not sigma, this is the sample standard deviation, the standard deviation of the sample. All right, so we don't have the population standard deviation. This is more realistic, we don't know it. We want a confidence level of 99%, which gives me an alpha of 0.01. So if I don't know sigma, then I have to do this t guy, right? So the margin of error then equals something like t times the standard error. Like t times some standard error. So we could go find this t using the norm inverse. The t inverse function. We're not going to do it that way. And then the standard error would just be what, s divided by the square root of n. Instead, we're going to do it using this confidence.t formula. Confidence.t, I just put in alpha, standard deviation, and n. I got those three things, they're just in the problem. Done. And then, just like before, I got to add or subtract that to the mean. Alright, so here's my x bar. For the upper confidence limit, I add the margin of error. And for the lower confidence limit, I subtract the margin of error. Done. And then we say we are 99% confident that the true population mean lies between 1.16 and 1.23. And then we're done with that one. So another version of this same type of problem is if we were given raw data. So I showed you this one in class too, but this problem is from the book 12.37. The problem says something like a company who makes razors went and sampled a bunch of people, a bunch of men, to ask how many shaves they get out of each razor. And they're interested in knowing what the population mean use of razors is. And this is important for them because they can tell how often they can sell a razor. All right, so there's two ways we could do this. We could go and just figure out a bunch of stuff. All right, we need to know the x bar, which is we just use equals average. Control shift down, hit enter. Standard deviation equals standard dev dot s, not standard dev dot p. This is the sample right here. Hit enter. N, how do I find n? That's just a count. I just count how many times there's a number there. So 212 times. What else? I guess I need I need some confidence level and an alpha. So I can't remember. In the book it probably tells us, but let's just say we have a 95% confidence level. And we'll do a 0.05 alpha. So from here I could just find the margin of error pretty easily, right? Using this confidence.t. Why am I using .t? Because I don't have the population standard deviation. I have a sample standard deviation, but not the population. So I have to do a t distribution. Here's my alpha. Here's my sample standard deviation. Here's my n. Got it. Upper confidence limit, lower confidence limit. X bar plus my margin of error. And x bar minus my margin of error. All right, here's another way to do the same problem then. We could just do this with the data analysis add-in. So we go to data, descriptive statistics, data analysis, descriptive statistics. Then okay. Input range, select all the data. And I put the label there. We want the summary statistics checked, and then here it is, confidence level for mean. So I can just check that and make sure it says the confidence level I want. So 95% is the default. That's what I want, so that's good. And then let's just put it where we want it, right there, and click on OK. And then we get the descriptive statistics like we're used to seeing. So here's our mean. This is our x bar, standard error. Where's s? Remember the standard error is just s divided by the square root of n. Where's n? Way down here. Count. Yep, there it is, standard error. So we could figure that out. Count is n. So this right here, confidence level, this is the margin of error. Same number we got right here. Those two are the same, right? So we could find it. If we have the raw data, we can do it this way, a little bit easier. We still have to do this upper control limit and lower control limit number, which in this case, here's our mean. And we just add our confidence level. And here's our mean. And we subtract the confidence level. That's it. So that works. So let's do one more. The last type to do this is with proportions. So sample, here's an example that was in the book. A sample of certified public accountants in one geographical region was asked if the FASB, Financial Accounting Standards Board, is too slow in issuing new accounting rules. So we sample 30, and is 30. 20 of those surveyed thought the FASB was too slow. So 20 were successful, you could think of that, where this is a binomial experiment. Success means that they thought it was too slow. So our proportion of success is 20 over 30. Yeah. Finding 90% confidence interval. estimating the proportion of CPAs in this region who feel that FASB is too slow in issuing new accounts. So remember, we surveyed 30 people, but there's way more than this. Maybe this is a big city or something. There's way more CPAs. So we're using this as a poll to try to estimate what the entire proportion of CPAs is. So we actually have everything we need here. We could find the margin of error. So there's actually one more thing that we could use. In fact, we need it. Is a standard deviation of the p hats, which I talked about this in class. This is just the square root of p hat times 1 minus p hat. That's it. That's a standard deviation of p hats. The standard error, we would divide that by the square root of n, right? Or divide that by n. All of it square rooted. But we're not. We're finding the standard deviation. The reason why is because if we use this confidence.norm formula, we need an alpha. Oh, I haven't figured out an alpha. Let's do that first. Let's see. Here's my confidence level. So I should put alpha right below it. Alpha equals 1 minus my confidence level. So we need an alpha. There he is. And a standard deviation, not a standard error this time. It's actually really standard deviation. And the size, there he is, 30. That's it. So that gives me a margin of error. So my upper control limit and lower control limit is the p hat. And this time my estimate is p hat plus my margin of error. And my p hat minus my margin of error. Remember, we're trying to estimate what the true proportion, what p is. So these upper and lower control limits can't be beyond, negative, can't go below 0 or above 1. Because a p, proportion of success, has to be between 0 and 1. So even though we might actually exceed those two, we shouldn't. So if our p hat was like 0.80, let's find a better one. Let's say our p hat was 0.95. So this upper control limit is 1.01. That has to actually go down to 1. If the answer was that, the upper control limit should be 1. We can never go above 1, right? So same thing, if I made this 0.05 or something, I can't have a lower control limit that's less than 0. So this would then just be 0, right? All right, that's it for these problems. Let's put this back. There we go. So good luck. Thanks. Bye-bye.